And FracTex is in this over here. So also here we have the same data set. As you can see, the same horizon, the same thin fault likelihood overlay. In this case, beefed up a little bit by computing the RMS of TFL. And we have a small seismic section. I first go into my attribute window in which I have defined a number of attributes. If I first look at the texture attributes, you can see here we have groups of attributes. If I look at all the attributes and go to texture attributes, we have two inputs. We have texture and texture directional attributes. So these are the basic ones, and these are the ones that have been added by Geo5 and in which you can compute texture in different directions. Let's first look at the basic one, texture. You have to specify an input seismic, you specify how much seismic you want to analyze around this position. In this case the time gate is -8 milliseconds above, 8 milliseconds below. You step out 3 samples in the inline direction on both sides, so that is a 7 samples input, same in the crossline direction. And you can do steering or not steering. If you do steering, then you will follow the seismic reflectors better than if you don't do the steering. You're just then extracting the information horizontally. Here you specify which GLCM attribute you want to compute, and you specify whether you want to compute a matrix based on 16 by 16 gray levels or 32 by 32. You need to compute the input data range, the minimum and the maximum, because that will then be transformed into gray levels. And then you get, in this case, a name, you assign it, and it becomes an attribute that you can use and play with. So I already played with this attribute and I showing it here. This is the texture contrast, and that looks like this. And if we now look at directional attributes, then it's slightly more inputs in the and outputs in the parameters here. So we again compute the number of gray levels. We need a min-max of the input data, which can be computed automatically. We define the window in inlines and crossline steps and vertically. And then here you can see we have many more attributes that can be computed in this particular case. Unique, of course, to this particular analysis is that you can specify the direction in which you want to compute these different attributes, and whether you want to use steering or not. You give it a name and you add it and you compute it, and I've done that here, and it looks in this particular case like this for this particular attribute, the directional correlation in all directions. Now, it may not look that interesting, but it becomes interesting, of course, if you are going to analyze it in FracTex, because in FracTex we have, for instance, this attribute, which is FracTex energy anisotropy. You have to open it to get more parameters. Here you have the number of directions in which you can compute, and you can increase that, but then you also have to increase the window analysis size, and the computation times become pretty large if you do that. So typically you would use 13 directions. We have these attributes that we can select now, GLCM attributes, and then we can output 2 attributes. One is the anisotropy factor, and the second one is the fracture dip azimuth. So the anisotropy factor again is the value from 1 or higher, and the higher it is, the more anisotropic the the image is at this location. And the fracture dip azimuth is the azimuth of the largest variation in anisotropy, and that should correspond to the fracture orientation. Again, you can do this full steering. You give it a name, and then here I have the different attributes: fracture, contrast, energy, inverse distance moment, entropy, and it's all anisotropy that I'm outputting. And here I'm outputting the corresponding fracture dip azimuths for the same attributes. Now this calculation takes quite some time, so I have computed a few up front, and this one, for instance, is the FracTex homogeneity anisotropy, and we can see that the highest anisotropy is in this area. If we compare this with the RMS of the TFL, then we can see, yes, not surprisingly, that there's a lot of anisotropy here, and actually this is an artifact. It's a typical edge effect we see with TFL calculations. It's not just our software, it is all softwares have that, and we actually have ways to minimize this. So, but it's still there, and that is also reflected here in the FracTex anisotropy calculation. But over here, where we have the real faults, it also scores high in terms of anisotropy. So this would be interesting to further evaluate. And more interesting, I think, is the fracture dip azimuth, which looks like this, and this picks up indeed the fault directions quite nicely. So this is one of the major outputs, main outputs of the FracTex analysis. And this you can do for all these different attributes. And if all goes well, then you pick up the anisotropy in the image. In this case, it is related to faults because there are real faults in the data. But if you are looking at a fractured reservoir, then there might be not any displacement, but still there might be anisotropy due to the fractures in the system. And that is the end of my presentation. So thank you very much.